the diceSum problem was very similar to the dice rolling problem that we started with. I'm going to open that slide back up for a minute here. The diceSum problem is right here. Oops, wait, why did that happen? No, I want to go to here. All right, sorry about that. We already have code that rolls dice and prints all the combinations of values. I want to now print the ones only that add up to a certain total. Okay? Now, I taught you kind of a mantra about thinking about backtracking problems. What are the 3 steps? What's the first step? Choose, explore, unchoose. Right. This is going to be like a chanting session today. That's how we're going to remember things. Yeah, so choose, explore, unchoose. Those are the 3 steps of backtracking. Now, we did that for dice. I'm going to pop open the code that we wrote last time so we can remember that code real quick. OK. Here we go. We wrote this diceRolls method and diceSum method. So let's remember the diceRolls code. One of the key things we learned last time is that usually the heading of the method, the heading of the function that you are asked to write, does not totally match the parameters that you wish you had. Okay? This is a common thing in recursion. And you'll actually see this on your homework 3 that you should be working on right now and on future assignments that involve recursion. And of course, what we do is if the heading we want is not the heading that we are asked to write, what's the heading Gotham needs right now? But whatever. Anyway, sorry. If you want the heading to have more parameters, you just write a different method, like a helper method that takes the parameters you want. And you have the required method call yours. Right? That's the trick we're learning. And in the case of backtracking, usually the extra parameter or parameters that we are adding is meant to remember things that we have chosen on previous calls. Because we're talking about choose, explore, unchoose. So if you get all the way down that tree of calls and you're the 4th or the 5th call, you need to somehow remember what did the 3 or 4 calls ahead of you do? What did they choose to do? Because your options might be based on that. Okay? So in the case of diceRolls, we're keeping a vector of die roll values that have been chosen in the past. And we're passing that along by reference to all of the later calls. And the choosing and the exploring and the unchoosing consists of adding a value to the chosen vector, exploring by making a subsequent recursive call, and then unchoosing by removing the element from the vector when we get back. Okay? That's the code we wrote. Now, diceSum is pretty much the same. The only difference is that once we get to the base case where there are no dice left to choose, instead of always printing the vector at that point, we will only print the vector if the sum of the things in the vector is the desired sum. Now, you guys told me how that's what we should change at the end of last lecture. Now, the easiest way to do that is you could just write some kind of method called like sum that takes a vector and adds up the values and returns a sum. So I don't think that's very interesting code. This is not related to recursion. So I just like wrote that real quick. And then I can just call that up here and say, well, if the sum of all the things in the chosen equals the desired sum, then I will print it. And what do you know? If I compile that and run it, I do get the dice. I believe I'm making a call of 3 dice trying to add up to a sum of 7. And I think I am getting that as the output here. So it seems like we're done. But I wanted to leave you last time with the idea that that might not be a good solution to the problem. And my concern is it's not efficient. And so what you discover with a lot of these backtracking problems is they need to explore a big tree of possibilities, possible paths, possible values, possible options that they could choose from. And it's really important to try to limit to plausible options that are likely to be successful, if you can. Sometimes you just want to do all of the options and print them all. That's fine. But on many problems, if you don't constrain yourself a little bit, then bad things will happen. The code will take too long. Now, this didn't take that long. I ran it, and the output appeared immediately. But I'm just trying to use this simple example to illustrate something that will be more important later. So how do we know that this is inefficient? Well, let me show you. How would we measure how efficient this was? I mean, we've talked about this algorithm analysis and big O type of stuff. But I think it's harder to apply that when you have recursion. I think what would be helpful for me would be to see how many total times does this function get called. That's a reasonable measure of how long it's taking, right? So if you want to count function calls, you have to do something kind of naughty. I like how a lot of you like looked up when I said that. They're like, ooh. Here we go. I'm going to do something bad here. And I just want to, I want to be clear that I'm doing something bad. Because I don't want you guys doing this, I just figure I should just show you this, because if I don't tell you about it, you're going to learn on the streets about it, and I don't want that, So you can have this thing called a global variable, and they're evil. And that's when you put a variable just outside of any of your functions. And the reason that's evil, I think you probably know, is just that it's too open to the world to be changed. It's like putting your valuables outside your house with no door locked around them. People can just come and mess with them, So if I said int calls equals 0 here, then in diceSum helper, I can say calls plus plus. So every call, it increases this thing, right? Now, you could accomplish counting the calls without this. I just am doing this because I want to very quickly just demonstrate how many calls there are, and then I want to delete this code again. That's why I'm temporarily doing this evil thing. I'm going to put it up here above main, actually, because what I want to do is I want to call diceSum, and then I want to print how many total calls there were after it's totally finished. So I'll say cout total calls, endl. Okay? So I'm going to compile that and run it. And it had 259 total calls. So I guess it's not really clear whether that's a good number or a bad number. I could try all the sum of 4 dice that add up to 9 or something like that and see how many calls that does. That prints a lot of lines, and it does 1,500 calls. I mean, again, these are numbers. It's bigger now, but I don't know if that's a bad number. Well, let's talk about this particular problem here. That's our code that we wrote, basically. This is why I think this is an inefficient solution. Some of the branches of this decision tree that we're walking through are not likely to lead to a successful outcome. In fact, they're demonstrably not going to lead to a successful outcome. And if you were going to try to describe that, I mean, look, I'm trying to add 3 dice and get a desired sum of 5 in this picture. And some of these red boxes here are bad ones, where we're not going to print anything, or we're not likely to print anything. Can you describe to me what are the sorts of situations where you know you're on a bad path in this tree? What's one of them? Yeah.
First of all, if like the first one you choose is like greater than 5.
Right, like over there on the top right of the call tree, the first die I picked 6, and if I'm adding up to a total of 5, I'm already over the limit, and you can't roll a negative number, so there's no way to get back down to 5 once I got up to 6. So if I wrote the code this way that we have here, our code is going to walk all the way down all of the possible things that could follow that 6. And that's completely wasted time, because none of those are going to lead to an output, right? So great, yeah, if the first thing we pick is too big, then yeah. And in fact, I would generalize what you said. It's not just having the first die be too big. If we roll a 4 on the first die and a 2 on the second die, there's no reason to roll the third die either, right? Because we've already reached 6. The third die can't get us back down to 5 with those 2 before it, right? So basically, if we get to a point where it's too big, that's no good. Are there any other paths, types of paths, that are not worth exploring? Yes, what do you say, sir? Yeah.
If you, like the sum of the dice you've already rolled plus 6 times the amount you will roll will not, is less than the desired number.
Yeah, well, he said the opposite problem. Like we just described being too high, and you're describing being too low. So an example would be like if I'm trying to roll 3 dice and get 15, and on the first die I pick a 1. If you just think about it for a second, the most I could possibly get with the other 2 die is 6 and 6, right? So that would be 12 plus 1, 13. I can't get to 15 no matter what. So why walk all down that tree looking for something that won't be found, right? I think our code could take advantage of these observations to avoid going down paths we don't need to go down. There's another source of inefficiency here, which has to do with this method that we're using called sumAll. I claim that that method, or that function that we're using there, is wasting a lot of computation that it doesn't need to be doing. Maybe it's not clear why I'm saying that. The method itself is not poorly written. It's just the way that we're calling it, the number of times we're calling it, and so on is too much. Do you know what I'm getting at? Is there some way we could avoid calling that method so much, or maybe not need it at all? What do you say?
If we're going to incorporate this new approach where we are already rejecting rolls that sum up to, I mean, maybe your proposal already uses sum all, but if we're already rejecting branches that don't sum up to the desired number, then we don't have to check that the branches we end up with sum up to the desired number because there are other options.
That's a great point. He says if we are, every time we go down the tree, if we're avoiding bad branches, maybe that means by the time we get to the bottom, we must be at a good branch. And so we could just print what we have. But, so I think you're right. That's a good instinct. So let's talk about how we would implement this idea of don't go down the branches where it's going to be too big or it's going to be too small. Okay? And I think the idea there is we have this notion of the sum so far, right? Like if I rolled a 6 so far, or I rolled a 4 and a 2 so far, then my sum so far is 6, and that's too big for 5, right? So this piece of code wants to look at the sum so far as part of guiding its computations now. And we don't have that available. We can do the sum of a vector, but that's the sum of everything. And so I think the better way to do this would be to add a parameter for the sum of what we've chosen so far. And we'll pass that along to each call. And the reason I like that solution is because we could figure out the sum of what we've chosen so far by looking at this vector and adding up all of its elements. But if we pass along the sum, I think that will be more efficient, because if the sum so far is 14 and we pick a 3, then now the sum so far is 17, and we don't have to loop over and add up that 17 again. We just know it. So my suggestion is to come here and say we have a desired sum. These are the first 2 parameters from the original function. We also have an int sum so far. Okay? When we call the function, what should we pass as the sum so far? 0, right? We haven't added anything at the start, so 0. So here's our sum. If you are going to make a recursive call, it means like, here's me, I'm a call. I have to roll this many. Oops, wow, what did I just do? Wow, cool. Whoa. OK, sorry. Well, now where did it go? Come back. OK, I won't touch it again. If I have this many dice that I need to roll, and I have this sum so far, down here is me. I'm picking that I rolled I for my die, and I'm making a subcall. I have to pass a sum so far here, right? What is that? What should I pass for that? It's what's before me plus what I have chosen, which is I, right? So it's the sum so far before me plus I. Do you understand? Like, that's the amount that I've contributed to the total with my call. OK? So now, at any point in this code, I know what the sum is so far. The whole point of that being a variable in our code is so that we can avoid bad paths in the code. So how do I do that? It seems like I don't always want to do this stuff, right? It seems like there's some sort of test, like if something, then I want to choose explore, unchoose. Bless you. What is the test right here? We need to avoid it being too small and being too big, right? So maybe we'll do the too big first. Yes?
If sum so far is greater than design sum.
So that's a case where we don't want to do anything. So maybe I'll say if it's less, I mean, yeah, you're right, but just I'll flip it because the condition where I want to call is where I haven't gone over, right? And that's a good start. I actually think we can be more precise than this because it's not, I mean, that's basically right, but it's not just that, right? Like, let's say I'm rolling 5 dice and I'm trying to get to a sum of 8. And I've already got a sum so far of 8 and I've only rolled 2 of the dice. Even though I have not gone over, I still don't need to explore because the minimum I can get is a 1 on every die, right? So I think maybe we could account, like, what I really want to know is if the minimum I could possibly get up to from this sum so far has exceeded the desired sum. You know, that's kind of what I mean. So the way I would say that is the sum so far plus, you know, if I rolled an I and the remaining dice were all ones, like if there was a 1 rolled by all the remaining dice, that would be the least I could possibly get if I chose I, right? So if that is at least as big as the desired sum, that's a good thing, right? I think we're trying to say the conditions for when we do want to make the call. Wait, did I do that right? Am I backwards? Wait, so minimum is less than or equal to the desired sum, right? I have to think about it for a second. And what's the most I could possibly roll if I chose I? It would be a 6 on all the other dice, right? So like if I had this sum so far, and I chose I, and I got a 6 on the remaining dice. Wait, so do I have this backward? I think that has to be at least as big as the desired sum, right? Do I have that right? If I roll the smallest possible thing, that has to be not too big. And if I roll the biggest possible thing, that has to be not too small. I think I did that right. We'll run it and try. It's OK. Luckily, we have a compiler, and we can run things. So that is going to hopefully help me avoid these bad outcomes. Another thing is this sum all of chosen. We don't need to call sum all anymore, right? What do I use instead of that? The sum so far at that point is the sum of everything. I don't need to loop and recompute it all. I already have it as a variable. So I avoid, basically, I don't need that method anymore. OK, let me make sure I actually did this properly. Oops, invalid what? Oh, sorry. The heading up here, the heading for dice helper, I didn't add in my int sum so far up here. You guys probably have that bug sometimes, right? Your helper, your prototype doesn't match the function. OK. Run. So let's observe that we are still getting the combinations. It's supposed to be 4 dice that add up to 9, and I am still getting that, right? The output seems to be right. And the number of calls is 140. I think it was like 1,500 before. Do you remember? It was something up in the thousands. So we just avoided like a whole bunch of these calls with that if statement there. And so this is a much more efficient version of the same program. And the difference would only become more and more pronounced each additional die we added to the call that we made. Because you're kind of splitting the tree by 6 every step down the tree. So it's kind of like a 6 to the k or something like that growth rate of the algorithm runtime. Anyway, I'm just pointing this out as an example where when you do backtracking, you often want to think a little bit about if you're going down a path that's not going to lead to anything useful. And you want to try to avoid doing that if you can. Okay? Any questions about that one? Yes, sir.
So, but aren't we checking a lot of if statements here? So we count the function calls, but we don't call the if statement checks.
I see. Yeah, it's a good point. Like, I mean, the if statement has a cost, having to check if every time we go down the tree. I guess what I would say to you, I mean, we could sit here and measure it with a runtime, like a millisecond measuring thing. I'm not going to take the time to do that right now. But what I'll say to you is the cost of those if statements is significantly less than the cost of walking down large branches of trees that are not going to be successful. Because 1 or 2 ifs might avoid me thousands of tree branches in a big call. Like if I did all the combinations of 12 dice that add up to 26 or something, we would be avoiding huge chunks of that tree for the cost of a couple of ifs here and there. I think it would be a big savings overall. But yeah, it's a good point. It's not a completely free operation to add this code. Yeah.
I was wondering, in the base case, do we have to check whether sum so far equals desired sum?
That's a good question. I mean, and I think the other gentleman also was talking about this. If we only make calls that are not too big and not too small, then when we get to the bottom, won't it just be the right sum? Because it won't be too big and it won't be. Well, let's find out. Let's see what it does. I took out the check here, so it's just going to print. When it gets full, it's just going to print it, no matter what. Looks pretty good. So this is a great observation that if you're only making calls that are within valid ranges, when you get down to the very end, you would only have made a call that put you in exactly the right place to get a sum of the desired sum. So yes, I'm glad you pointed that out. That's even better. So it's even a little more efficient than it was. Great.